Hello guys, in this video me and my teams will be describing the English to French neural machine translation system which was implemented using sequence-to-sequence architecture with Bahdanau attention in TensorFlow. So the main objective of our project was to build a model that can automatically generate the appropriate French translation to a given English sentence without relying on the external translation APIs. Instead, the model will learn the mapping directly from the data using supervised learning. So in this video, firstly we'll briefly introduce the dataset and the preprocessing steps. Secondly, we'll explain the encoder-decoder model and the attention mechanism. Thirdly, we'll discuss the training process as well as the evaluation matrices. And then lastly, we're going to show the qualitative results as well as with the attention visualizations and summarize the key outcomes of our project. So for this work, we used a English-French parallel corpus which we derived from a ManyThings Tatoeba project, where each line contains the English sentence along with its French translation separated by a tag. We preprocess the data by converting all the text into lower cases, removing any extra white spaces and discarding the sentences that exceed the chosen maximum length. Now this will help us to control the training time and the model complexity on the standard systems. Separate tokenizers are fitted for both English and French, and sentences are converted into integer sequences, and a zero padding is applied to obtain a fixed length input tensors for both encoder and decoder. Now this is all about the brief introduction to dataset and the preprocessing steps. Next we'll move on to model architecture.
The core of a system is a sequential to sequential model which contains Bahdanau attention and encoder-decoder structure. So this design is widely used because it can read any length of input and output sequence and can understand the complex mappings between the encoder processes the English sentence. It consists of an embedding layer followed by an unidirectional LSTM, which stands for long short-term memory. The embedding layer transforms each token index into a dense vector representation, and the LSTM reads these embedding sequentially, producing a hidden state and followed by producing a hidden state for overall input sentence. The decoder generates the French translation one token at a time. It also contains an embedding layer and an LSTM, but it is augmented with an explicit. At each decoding step, the decoder uses its current hidden state to calculate the relevant scores over the encoder hidden states, and then it is normalized with the softmax function to calculate the mechanism weights, which then strongly tells us how to focus on the source position. The attention weights are then used to form the context vector, which is said to be the weighted sum of the encoder hidden state. The context vector is concatenated with the current input embedding layer and decoder LSTM. This mechanism allows the model to dynamically attend the different parts of the input sentence while generating the output word for each, while increasing the translational quality even for the complex sentences. Now we will discuss how we train the model and how we evaluated the performance.
First, the code loads an English to French dataset and cleans the text. It removes long sentences for easier training and limits the dataset to 10,000 pairs. Then it converts all the words into numbers using tokenizers and pad sentences so they all have the same length. French sentences also get start and end tokens for the decoder to know when to begin and stop. It uses teacher forcing during training and optimized using the Adam optimizer with sparse categorical cross-entropy loss. Padding tokens are masked so they don't affect loss. After training, the model can translate new English sentences. The code evaluates performance using token level accuracy, ROC AUC, word level and sentence level accuracy, sample translation outputs. Finally, attention maps and ROC curves are plotted, and an interactive mode allows user to input English sentences and a French translation.
In our project of the simple English to French translation model using the sequence-to-sequence architecture, after training, for the performance evaluation, we use both qualitative and quantitative methods. So, in the training process, we used around 30 epochs, and then the loss function kept on decreasing, and then till it reached 0.31, which is a very low curve or a decreasing curve that shows that the convergence is very good, and also it interprets that the model is learning the patterns of both the English and the French meanings, like, and understanding the patterns, and also giving us not just random guesses. It also interprets that the encoder and decoder is working efficiently. In the validation set, we validated two important metrics, that is the token level accuracy and the ROC AUC. The token level accuracy was moderate, that was 54.52%, and the ROC AUC was very high, that came to be 0.969. This shows that the model was able to distinguish the incorrect and correct words very accurately, and also it shows that the model was able to like understand the patterns in the sentences correctly. It also, some mistakes may be due to the vocabulary size and the language complexity. It is not due to the training of the model. We also calculated the word level accuracy and the sentence level accuracy. The word level accuracy was 84.88%. That means that 85 out of 100 words were correct. And the sentence level accuracy was 79.45%. This means that around 58 out of 70 sentences were correct. This is very impressive and also shows that the model doesn't just understand words but understands full complete sentences when we translate it from English to French. These are the sample translations that shows the translation from English to French. Here the English word is hello, and the French that the actual word should be is bonjour, but our model predicts is au revoir. Again, here we have English word hi, and the actual is supposed to be like salut, and the predicted word from the model is salut. That is correct. Again, here it's like good morning, and the true meaning should be like bonjour, and what our model predicts is bonjour. So this translation is correct and natural in French. That shows that model correctly understands the intent of the sentence, the proper form of word order in English, and the correct use of verb. The most important results in this project is the attention heat map visualization. That shows that in the x-axis it's the English words, and in the y-axis we have the French words. For example, here it's like in the y-axis we have où est le hôpital, and here it is where is the hospital, that is in the English translation. So the darker regions, like it shows that it means that it's like the attention that has higher scores. So when the model translates the word le hôpital, it strongly focuses on the English word hospital. This confirms that the attention mechanism is working and helps the word align properly to the French meaning. The ROC curve plotted for the project clearly shows 0.969, that is clearly above the diagonal, as can be seen here. That means that the model predicts very accurately and the results are very good. This is the data loading and pre-processing step. Here we load the data set that we can see as fra.text here. This converts the entire text into a clean numeric training format for the model. Next is the training, validation and test split. This ensures the model trains with one part and is evaluated fairly on unseen data. The sequence-to-sequence model architecture that includes the encoder, decoder and the attention ensures that embedding layer turns word IDs into vectors. LSTM reads the entire English sentence and outputs encoder hidden states and also the final states. The Bahdanau attention helps the decoder focus on relevant English words at each steps. That allows alignment between the decoder state and the encoder states. Decoder uses the previous word, attention content, and the previous hidden states. The entire thing translates the sequence into another language by learning content. The training loop feeds true previous word to the decoder instead of predicting words. It computes mask loss and applies backpropagation using an Adam optimizer. It minimizes translation error between the model predictions and real target sentences. The translation inference function, this encodes input sentences, starts decoding with start token, predicts the next token until end or max length reached, also collects attention weights for visualization. It translates user-centered English sentences into French. Here the evaluation of the token accuracy and the ROC AUC takes place. The token level accuracy measures how many predicted words match to true tokens. The ROC AUC evaluates the classification quality across all target vocabulary classes. Quantitatively measures translation quality. The ROC curve plotting uses validation predictions and flattens all probabilities and true labels. that plots micro average ROC curve.